So let's talk about an equation that we've talked about before, or at least thought about before. Let's look at dx dt is equal to x. So this is a differential equation. Nobody would argue with that. We know that the slope of x of t, which is what we're trying to find, don't forget, what we really seek to find is x of t. X is a function of time, but the change of dx with respect to t, in other words, the slope of my answer, the slope of the graph that I'm after, is going to be equal to whatever value of x I'm at. So before we actually get to trying to look how to solve this, as far as graphing it, let's go ahead and solve it by separation of variables, because I want to point something out in the answer and I want to go through that step by step. So let's just go ahead and solve this, and not even talking about graphing, we'll just separate variables and do it. So we can move x over here and we can move dt over here. So what we'll have is 1 over x dx is equal to dt. Make sure you understand that. All we did was move the dt over here, right? And we take the x and divide, so we get 1 over x. So we can integrate both sides of this guy. So we'll have the integral of 1 over x dx is equal to dt. And I can integrate this because the integral of 1 over x is natural log of x is equal to, whoops, I got to integrate that side too, is integral to t plus a constant. So I've integrated the right-hand side. All right. Now, in order to get x outside from being wrapped up in this logarithm, I need to raise both sides to the power of e. So it's the natural log of x is equal to e t plus a constant. This is all inside the exponential here. So I raise both sides to the power of e, and what that does on the left is this absolute value of x just comes right out. And on the right-hand side, I can rewrite this a little bit. I'm going to write it as e to the power of c times e to the power of t, because really these are added together, so I can split it up because this is basically equivalent. C plus t is right there. So when I multiply two exponents together, I add the exponents. I'm just doing the reverse and splitting it apart. The reason I'm going to do that is because I'm going to leave this as absolute value of x is equal to e to the power of c. This is just my constant of integration. I'm going to call that constant k. This whole thing, e to the power of c, I'm going to call it constant k. All right, e to the power of t. All right, so that's really our answer, but notice that we still have this absolute value here. So to be totally rigorous about it, what this is basically telling me is that x of t, which is what I'm really trying to find, is equal to plus or minus k e to the t. Now, even this is a little bit ambiguous, or a little bit not necessary to put plus and minus here, really, because even if you write it without the plus and minus, k is a constant of integration. K can be any value at all. It could be positive values, could be negative values. So it's a little bit redundant to put plus or minus in front of the k, because k can take on any value at all. So really, when you go from this absolute value step to this step, you really don't have to put this here, but I'm putting it here to be totally explicit about something that I'm going to point out to you a little bit later. So what I want to do is just sort of circle this, because I'm going to use it to show you something pretty cool. Now, we have solved this differential equation. This is a general solution of the differential equation. Let me write this down. General solution. What general solution means is that there's an infinite number of solutions here corresponding to different values of this constant, really corresponding to different values of an initial condition, because I can have any initial condition I want. This describes all solutions with all initial conditions. So right now we're going to leave it like that. We're going to go over to the other board, and believe it or not, we are actually going to graph this differential equation without even looking at the answer. And then once we get the graph on the board, I want to show you some cool things relating to what the graph looks like in relation to what the solution really is. That's why we did this first. But in general, what I'm teaching you here is you don't really have to solve it to do any of this stuff. Let's look at the differential equation again. Let's pretend all we have is the following. Dx dt is equal to x. And we're told to graph it there. So we want to graph x of t. So we want to graph x of t. That's what we're trying to graph. And we've actually calculated the solution over there, but we're not going to look at that right now. What we notice right away, because this solution is first order and it's so simple, and this is really the key to really using this technique, is that we can read a whole lot into what it's going to look like just by looking at the differential equation. Because what it's telling us is that, yeah, I'm trying to find the graph of this function here, but I don't know much about this function, but I know a whole lot about the slope of that function. because I know that the slope of the answer that I seek is just equal to numerically the value of x that I have. In other words, if I attack it a different way, if I just start picking some values, let's say I say, all right, well, let's just pick a few values here. X is equal to 0. Then that means that dx dt, which I'm going to say is the slope m of my function that I'm interested in, is going to also equal 0, because the slope of my answer is actually equal to numerically the value of x. And if I pick another value, x is equal to 1, then the slope, dx dt, which is just the value of the slope of my answer, is going to also equal 1. And if I pick x is equal to 2, let's say, well, let's actually pick x is equal to negative 1. Then dx dt is going to equal to minus 1. So you might be able to follow this, but not really able to see why this really matters. Let's go ahead and draw a coordinate axis and see if we can make some sense of this. So let me draw this like this. Now this is the t-axis, and this is x of t. So really I am trying to graph the actual solution the way it sits. Now you really do need to open your eyes and look at what we've written down up here. What we're basically saying, pick this guy right here. Actually, let's look at the second one first. When x is equal to 1, at all values, when x is equal to 1, the slope of the answer that I'm seeking is also going to equal to 1. So if I were to come on in here and put, let me go ahead and pick a light color here. Let's pick a light color here. This is going to be, let's say this is going to be 1, and this is going to be 2, and this is going to be negative 1, and this is going to be negative 2. Okay? So you have to use your imagination a little bit because I have to use a lot of colors. But at x is equal to 1, this is an equation of a line, folks. Don't forget about that. X is equal to 1. That is an equation of a line. It means all values horizontally, right here, I'm going to just try to do a little bit light so I'm not over-dominating the graph here. At all values at x is equal to 1, the slope of my answer is also equal to 1. The slope of my answer is also equal to 1. So remember, if a slope is equal to 1, that means that it's right here at 45 degrees. If a slope is 2, it's somewhere up higher. If it's 3, it's higher. If the slope is like 5,000, it's almost vertical. If the slope is very low, it's shallow. But when the slope is equal to 1, it's at 45 degrees. So right here at this line, I'm going to draw a little slash mark at 45 degrees, and I'm going to put it everywhere along this line. And I'll explain why I'm doing that here in a second. Hopefully you see it yourself, but if not, I will point it out to you. What we are saying is that I don't know what the general shape of the entire solution is, but I have shown myself, because of the way the equation is written, that at x is equal to 1, at all values of x is equal to 1, the slope of the answer I seek is also equal to 1. So I'm drawing little line segments with a slope of 1. Now let's go on down here. When x is equal to negative 1, all values of x equaling negative 1, all values of x is equal to negative 1, the slope is equal to minus 1. The slope is equal to minus 1. The slope equaling negative 1 goes the other direction. So I'm going to do 45 degrees this way. And I'm going to draw them everywhere because this slope is valid on this portion or region right here. I'm doing my best. I mean, you're not going to get it exact. Just do your best to slant it in the general direction. Now let's go ahead and look over here at x is equal to 0, which is just the line that really, covers up the axis here, right? And when we do that, oops, I already messed up my color scheme. That's okay. When I do that, the slope is also equal to 0. So everywhere here, the slope is equal to 0. So I have flat lines, because don't forget, a slope of 0 is totally flat. So I have flat lines here, like this. Now let's do some labeling so that we can make sure we understand. So here, let's do some labeling here. So here we have this x is equal to 1, the slope is equal to 1. Here we have x is equal to 0, the slope is equal to 0 of my solution. Here we have x is equal to -1, the slope is equal to -1. Do you see a pattern here? Well, this equation is so darn easy that the pattern is really obvious. Whatever horizontal line I choose here, I can draw a horizontal line anywhere I want. I'm going to draw little hash marks through it corresponding to the slope corresponding to the value of x that I'm drawing at. So if I wanted to pick another one, let's say at 1/2 here, I could draw, or -1/2 here, right? Then I would have another guy, because this is -1, so this is -1/2, right? So if I had -1/2, I'm not going to have a slope quite like this. It's going to be less than that. It's going to be shallower because I'm at -1/2, and this is a shallower slope. So here it would be more like that. See how this one is steeper and this one is not as steep. So I'm going to go -1/2 like that. It doesn't really matter exactly where you draw them. Just kind of give yourself a feel for what it's going to look like. So you see this is steeper in the negative direction than this. And if I go on and do one at +1/2, which is like right here, right? Then I'm going to have one +1/2. Then I'm going to have in this direction, I'm not going to have one quite as steep as this. I'm going to have one shallower because it's 1/2. So I'm going to be more like this. All right? Let me draw a few of these. And let me do one more, just to be totally clear. This is number 2. So if I'm at x is equal to 2, if I'm following the pattern, my slope is going to also be equal to 2. It's going to be really steep. So we need something super steep here. So let me go ahead and put, as steep as I can anyway. I'm going to do something like this. You're not going to be exact with this. This is not a quantitative solution. It's totally qualitative. But you see what's happening here. When you step back and look at what's happening here, then you can sort of see that if I'm tracing the little line segments, it kind of comes in like this. It's kind of like this, right? And then when I get below this line, it kind of goes like this, right? So if I were going to draw a few solutions here, it would look something like this. I would come like this. And maybe I'd have another solution that goes like this. Maybe I'd have another solution that goes like this. On the bottom side, maybe I'd have a solution like this. Maybe I'd have one like this, like this. Over here, it doesn't change anything. I'm just going to go up like this. Here, I'm going to go down like this. So you see, I get a family of curves is really what I'm trying to show you. The black lines really are x of t. So these guys, right, I'm just going to draw me a little arrow. Those are the solutions that you really seek. X of t is equal to that. Now let's take a step back and label and do a little bit more labeling. Here we had x is equal to 2, m is equal to 2. Here we had x is equal to 1/2, m is equal to 1/2 right there. And then we had -1/2 down below. But what you basically do is you try to look at your differential equation and you try to figure out if there's basically a way that you can find these lines of constant slope. See, this is what we call a line of constant slope. In other words, because the solution is so easy in this particular case, we're able to sort of pull it out of our thin air right there. But when you're looking at it, every curve, every little x of t that goes through here, even though I haven't drawn them all perfectly, they're basically going to have exactly the same slope along this line. Along this line right here, they're going to have exactly the same slope. The slope along this line is 2. The slope along this line is 1. The slope along this line is 1/2. The slope along this line is 0, -1/2, -1, -2, and so on and so on. These lines right here, these horizontal ones, is very important to understand what you're looking at. These horizontal lines are not part of the solution. They're not part of the solution. They're tools to help you graph the solution. The black lines are the solution. So the black lines are the solution there. Now, one thing I want to show you is, let's go back and look at what we actually got for the answer. When we solved this guy, we got an equation that looked like this. X of t is plus or minus k times e to the t. K can be anything. It's an undetermined constant because we haven't identified any initial conditions here. So if we pick values of k, let's say k is equal to 1, then we'll just have e of t plus or minus e of t. Then your solution will be this curve right here. These two black ones go together. They're mirror images of each other, plus or minus e to the power of t. That is this one right there. And if your initial condition produced a k of 1, this would be the only solution that you cared about. Okay? If the initial condition that you had produced a k of 2, then maybe your curve is over here somewhere, but it still looks the same. It's just sort of shifted over a little bit because of the way it is. I guess what I'm trying to tell you is if you pull a computer up and you stick this function in the computer and pick different values of k, you're basically going to get these different black curves that I've drawn here on the board. And that is why it's significant. When you use this method, you're going to end up finding an entire family of solutions. The reason you find a family of solutions is because the general solution of the differential equation is a family of solutions. It's an infinite number of solutions. So if I draw more and more of these black lines, I can draw them anywhere because there's literally an infinite number of solutions. So this is a really cool way to visualize what we've been doing all this time. We've been solving these differential equations and getting the answer, and the answer has always had these constants of well, really they're constants of integration, really, but they end up being constants here. And we kept telling you this is a general solution. There's an infinite number of solutions, and you really couldn't quite understand, well, how could there be infinite solutions, et cetera, et cetera. This is the reason why, because when you look at the graph of them, this differential equation without any initial conditions anywhere is only going to give you an infinite family of black curves, basically. If you lock down an initial condition, then one of these black curves will be your unique solution. And that's why I wanted to solve this first. It's the only reason why, so I could show you on the graph that these family of curves corresponds mathematically to the solution that we find when we solve it by hand. Now there's one more thing I want to show you before we erase this and go on to the next problem. All right, and that is to make sure you understand the difference between these horizontal lines and these black lines. And I've said it a few times. The horizontal lines are only tools. They're tools to let us cut these little line segment slopes everywhere, so we can sort of see a pattern and sort of see what the sort of the overall thing is, so we can kind of draw between the dots, so to speak, and draw our black lines as our solution. But these horizontal lines, I'm going to go ahead and write it in purple because I wrote these lines in purple. These are called isoclines. And you're going to see this in your book, isoclines. It's got a fancy word, and so people look at it sometimes and they're like, what does this mean? All it means is it's a line of constant slope. And in fact, I'm not even going to call it a line. I'm going to call it a curve of constant slope. Because in this particular case, the isoclines happen to be nice horizontal lines, and that made it very, very easy to do. But in future problems, the isoclines may not be straight, they might be curved. And that's just really going to get a little bit too difficult to describe without actually showing you a problem, but just trust me on that. So these isoclines are curves of constant slope, or lines of constant slope, if we're looking at this problem. And I sort of didn't introduce the concept of isoclines to you right in the beginning as we were doing all this stuff up here, because I really didn't want you to get too bogged down in terminology. But the way you're basically going to do this for future problems, sort of the proper sequence, is our differential equation was dx dt was equal to x, right? And we used some deductive reasoning to pick different values of x and so on, and figure out what the slope was. Really what you're going to do in order to have a bulletproof way of finding these isoclines and finding these curves is really what you're going to do is you're going to set the slope equal to a constant, because we want to find these lines where the slope is constant. We want to find these lines where the slope is constant so we can draw them, so we can draw the black lines in between them. So this guy, dx dt, that is the slope we seek. So we basically set dx dt equal to just some constant m. We use m because that's traditionally what you use in algebra to be the slope. Your book might use k. A couple of books I have on the shelf use k for isocline. I use m because it makes more sense because it's a slope. So if we set this guy equal to m, then all you have to do at this point, you're putting m in here, you just say m is equal to x, or if you want to flip it around, x is equal to m. These are the isoclines for this problem. These are the isoclines for this problem. What it means is that the isoclines are all lines with the equation x is equal to m. M could be whatever. I could pick m is equal, let's do it. Let's pick m is equal to 1. Let's put m is equal to 1 in here. Then I have an isocline at x is equal to 1. Well, here's your isocline. X is equal to 1. The value of the slope at this isocline is m. m is equal to 1. That's what I chose. If I choose m was equal to 0, then that slope exists along the curve x is equal to 0. X is equal to 0 is right here, and I put these little horizontal lines because m was equal to 0 there. If I put m is equal to 2 up here, the slope is equal to 2, then that exists along the curve of constant slope x is equal to 2. X is equal to 2 is up here, slope m is equal to 2, so I draw the slope. If I put a slope of 59 in there, that's going to occur along the constant curve x is equal to 59, which is way up high, horizontal line x is equal to 59. My slope will be super, super steep up there because of that. So this is what we're going to do in the subsequent problems. I could have started you off by doing it like that here. Whichever way you find easier, it's really exactly the same thing. Let's go ahead and flip the board over, and you'll get some practice with it and see how to apply it. So let's say our next equation looks a little bit different. dx dt is equal to t plus the number 1. Looks like a pretty simple differential equation, and it is. And we could solve this. I mean, we could do separation of variables. We could solve it. We could get the real solution. But I'm going to show you, how to graph it like we've been doing without ever actually doing that. So, step number 1. Let's find the isoclines. And don't forget, isoclines are just the curves or lines, depending on how complicated your equation is, where the slope of my answer is a constant. You can think of the isoclines like in the weather map. It's sort of like the little lines of constant pressure, right? Or if you're looking at a terrain map, of a topographic map or something, the lines of the little circles, or as you go up a mountain, the little circles of constant elevation. The isoclines are just the curves of the lines that are constant slope in my answer. The easiest way to do it is just to take the derivative that I have, dx dt, and set it equal to a constant, because I'm trying to find the curves where this guy is a constant. So I just set this equal to a constant. The constant I choose is m, and I set it equal to t plus 1. In other words, I just plug it in there. That's all I do. Now this is the slope that I seek. So let me solve for t. T is equal to, if I scoot this guy over, it'll have m minus 1. These are the equations of the isoclines. Now look at this guy and tell me, what kind of curve is that, or is it a curve? If I'm plotting x and t, and I have an equation, t is equal to something, these are vertical lines. These are vertical lines, right? How do I find the equation of these lines? Well, let's go ahead and do that right now. Let's go ahead and do that right now. So we're going to draw a nice coordinate axis here. And this is going to be t, and this is going to be x of t. All right. So before we get too far into this, let me keep a little bit of space on the bottom here. And let's go ahead and pick some values. Let's pick a value of, just to be cute here, there's many different ways you could do this. We could pick values of slope here, 0, 1, 2, 3, 4, 5, etc. And we could find values of t is equal to that. We could put in values of t and get values of m. It's either way you want to do it. Let's go ahead and pick values of m. So at m is equal to 0, right? Let me go ahead and rewrite my equation. I have t is equal to m minus 1. These are the isoclines. So at m is equal to 0, t is equal to minus 1. At m is equal to 1, right here, t is equal to 0. At m is equal to 2, 2 minus 1 is 1. T is equal to 1. Well, let's go the other direction. Let's say I have, let's go one more. M is equal to 3. T is equal to 2. And let's continue over here. M is equal to negative 1. If I put negative 1 in here, negative 1 minus 1, then t is equal to negative 2. Let's pick one more. T is equal to negative 2. Negative 2 minus 1, t is equal to negative 3. All right. So we have everything we need to really graph the solution right here. So we have a bunch of vertical lines. T is equal to 0. T is equal to 1. T is equal to 2. T is equal to negative 1. T is equal to negative 2. T is equal to negative 3. We've got them all right there. Okay, so let's go ahead and write a few of these guys here. Let's say we have, this is 1, this is 2, this is 3, this is -1, this is -2, this is -3, like that. And let's look at what we really have here. So at the vertical line, t is equal to 0, right? At the vertical line, t is equal to 0, which is this guy right here. These are vertical lines. The isoclines in this problem happen to be vertical lines. Let me switch colors here. Then at t is equal to 0, this vertical line, let me go ahead and write t is equal to 0 just to make sure you know that that's that isocline. M is equal to 1. So I'm going to go ahead and write m is equal to 1. So m is equal to 1. So the slope is equal to 1, 45 degrees. So let's do it. 45 degrees there, 45 degrees. Just do the best you can. Not going to be perfect. Just do the best you can. See, actually, these are a little bit shallow here at the bottom. But my advice is really don't get too wrapped up in it, because if you sit here and try to make them perfect, you're just gonna beat your head against the wall for no reason. All right, let's go to t is equal to 1. This vertical line, t is equal to 1. So let me draw a little vertical line here. T is equal to 1. Then that isocline, the slope is equal to 2, which is steeper. So you just do your best. If this is a slope of 1, you know, do a slope of 2 up a little bit higher, something like this. Let me change colors. So we'll do something like this. Something a little bit steeper than the previous line. Right? Something like that. Just do your best. Okay. Now we look at t is equal to 2 over here, this vertical line. And in that case, the slope is even higher. M is equal to 3. So we're getting pretty darn vertical. Maybe a little bit difficult for you to draw these guys. But you really want to show that it's shallow, steeper, steepest, like this. T is equal to 2. Okay, now let's go ahead and look over here on the negative side. When t is equal to -1, we have this isocline over here. So let me go ahead and draw a vertical line here. T is equal to -1. This isocline, m is equal to 0. That means there's really no slope at all for this guy. So we're going to go horizontal. So you see it starts to change direction, like that. Now at t is equal to -2, this guy, this isocline right here, t is equal to -2, the slope is equal to -1, which is 45 degrees in the other direction. So it's in this direction. Make it black. We'll do it like this. Okay, 45 degrees, more or less. All right, and finally, t is equal to -3. This is a a vertical line, t is equal to -3. Then you have -2 slope, which is steeper, but in this direction over here. So we'll go black, and we'll go a little bit steeper, something like this. Okay, so what you have here is a little, solution field, really. And to actually look at the solutions, what is it going to look like? Well, if you just kind of follow your pencil, you've got stuff coming in like this. It gets flat here, and then it gets really steep over there. Comes in, gets flat here, gets really steep over there. Comes in, gets flat here, gets really steep over there. And that's what the solution looks like. So in this case, these guys right here, these are my x of t's. This is my solution family. In other words, I have an infinite number of solutions, because if I were to solve this differential equation without any initial conditions, I would have a constant in there. And that mathematically, that constant would allow me to have all of these different solutions, much like we talked about in the previous problem. So whenever you provide an initial condition and you plug in and solve for that particular value of constant that you have in your solution, you're going to nail this problem down to take out only one of these solution curves as your family. But you can sort of see that it's parabolic, sort of, in general shape. So it's not something that's going to give you a bulletproof, precise answer, but it's really an instructive way to look and see how these things are really constructed, see what they're really doing, and also how it relates to the constant in the general solution. And it's a quick way to be able to get a general idea for how the solution is going to look. Now let's do one more. That's going to be a little bit more, I don't want to say it's complicated, but it's, we need to be a little bit careful about what we do here. Final problem. dx dt is equal to x squared plus t, x squared plus t. So this is a little different because I have a square term in here. It's going to be a little bit more, but the process is really the same. I need to find the isoclines. So to find the isoclines, I just take this dx dt and I replace it with a constant because I'm looking for curves of constant slope. So I'm going to replace this with m. m is equal to x squared plus t. m is equal to x squared plus t. Now, this isn't really that instructive when I write it this way because don't forget, we're really trying to find x of t. So let me move x to one side and kind of jockey it around a little bit. So what we really have is x squared is equal to m minus t. Because if we take this guy and leave it there, we move t over here, we'll have m minus t, and we sort of flip it around. This is what we're really left with. So these are the isoclines. These are the lines, or the curves. See, in this case, they're not lines anymore because you have x squared here. You know it's definitely not going to be a straight line if you have a square anywhere. So these are the curves. What I was trying to tell you, they're not always lines. They're curves sometimes. Curves of constant slope in my final solution that I'm trying to find. And the question you need to ask yourself is, what does this curve really look like? Now, you can go to a graphing calculator and you can plot it. But I think it's not going to be huge rocket science for you to understand that this is going to be some sort of parabolic shape because I have an x squared here. The only thing that makes it really tricky is that these are sort of sideways parabolas. In other words, if I had the parabola x is equal to t squared, then it would just be a parabola like this. It'd be really easy. But that's not what I have. I have x squared is equal to m minus t. So an easier way to really manipulate this, because I have an x squared, I mean, I could take a square root of both sides and try to plot it with plus and minus square roots. But really, if I just sort of take this guy and flip it around where t is on one side, so if I put it so it's t is equal to m minus x squared like this, and just sort of work with this, it's going to be a little bit weird, but I promise you that it'll let you visualize the isoclines a little bit better. Let's say m is equal to 0. Let's take the special case when m is equal to 0 so that I can more easily visualize it. Then t would be negative x squared. Now you're going to have to believe me a little bit when I say it's a sideways parabola. Let me draw it first and then I'll be able to better explain it. This parabola looks like this. It comes in like this and it touches the 0 point there and it goes back out. So this is the case when m is equal to 0. That's the isocline when m is equal to 0. Don't worry about putting the hash marks yet. I just want you to understand the shape of the isocline. If you turn your head sideways and think about it for a second, if x gets bigger, goes bigger, or in the positive or in the negative direction here, and you square it, you're going to get a big number. And then so you're going to get this big number and you stick a negative sign on front. So that means t is going to be getting negative big no matter what x squared, which direction x squared goes. So if x gets bigger, 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 t is going to get bigger negatively. So t is going to get bigger negatively. As I go bigger, bigger, bigger x, t is going to get bigger but in the negative direction. Don't forget, this is negative t here. This is negative t here. If I go x negative big in the negative direction, down this direction, then I'm squaring it, so I'm still going to have t getting bigger in the negative direction. So if you kind of tilt your head a little bit and look at this, you should be able to convince yourself that for the special case that m is equal to 0, you'll have this curve corresponding to the shape there. Now, if that doesn't make any sense to you, you could start here. You could take the square root of both sides, and you're going to get a plus minus square root, and you'll be able to plot the isoclines that way. That's fine. This is just a different way to visualize it. So what we found is that at m is equal to 0, the isocline looks just like this. When x is equal to 0, t is equal to 0. So this isocline touches right there. And at that point, the slope, or along this curve, I should say, the slope of my solution is 0, which is a totally horizontal line. So I'm just going to come through here and put horizontal lines everywhere. Okay? So along this isocline, my slope is 0. Now what happens if I have a slope, an m, let's say, of, let's say an m is equal to 1. If I put m is equal to 1 in here, then t is equal to 1 minus x squared. In other words, it's exactly the same graph as I had before when m is equal to 0, except I have sort of a bias added to it. I'm adding in the t direction of 1. So what's going to happen there, if you go and look at that isocline, is I'm going to have, this is going to be 1. So in this case, the parabola is going to look like this, right? At m is equal to 1. So just think of it this way. If I add something to it, I'm just going to have the graph that I just drew here, but I'm going to be shifting it this way because I'm adding 1 to it. In other words, I'm adding 1 unit of time to it, so I'm shifting the whole thing this way. Again, if that's a little confusing, you can always go back here, plug in different values for m right here. You'll have a square root, you'll have plus or minus square root. If you graph it, you're going to get the same thing. So I'm not really trying to show you any new fancy math. I'm just trying to get you to be able to visualize the graph a little bit easier. Now along this isocline, m is equal to 1, which is a 45-degree deal, which is more like that. Actually, it's a little bit steeper than that. So let's go ahead and do that. We'll put it there, and we will say something like this. So we'll try to do our best to do 45 degrees like this. And it gets a little bit tricky to do it, especially when you're on a curve like this, to kind of keep it consistent, because you can kind of see here, I probably didn't hold it totally constant, but I just did the best I could. All right, let's skip down here to try to save a little bit of space. What about when m is equal to 2? When m is equal to 2, then t is going to be 2 minus x squared. So it's the exact same curve, but I shifted over two t units to the right. So here is t is equal to 2. And so this parabola is going to come in and go out like this. And the graph is going to be even steeper. It's going to be something like this. T is equal to 2. M is equal to 2. Something like that. Not totally perfect, especially down here. I didn't quite make them steep enough. Something like this, okay? Let me try to go ahead and connect my isocline here. Okay, now let's go in the negative direction. Let's say m is equal to -1. So then t is going to be -1 minus x squared. So it's the same graph I started with, and I shift it this direction now. So if this is -1, then this isocline is going to come in like this, okay? And the slope here is going to be -1, which is 45 degrees facing in this direction, which is more or less like this. So I'm going to try to do my best and come in like this. Something like that, all right? And then moving right along, we'll say m is equal to -2, so t is equal to -2 minus x squared. So it's the same thing, shifted 2 units. I think you see the pattern here, -2. So here's my isocline coming in. -2 is even steeper. So do my direction, my best to go and do something steep here. Okay, so we've got a crazy looking graph really when you think about it. And we need to do our best to draw something through there. So the best thing is to try to start sort of at the top. Here you've got something going like, you see how these guys are kind of coming together? I've got these guys kind of coming together. So this is going to more or less be something that looks like this here. I'm going to have something that's kind of coming like this, all right? Now, on the other side, it's going to be kind of doing something like this. So this is going to be more or less something like this, something like this. And everything is going to sort of be meeting, to kind of get a little bit steeper here, like this. So you see how it's kind of hard to see with the blue there, but it's basically trying to show you the blue is going off like this, and the blue is going like this. So they're very curvy, very cool looking solutions. And again, there's an infinite family of them because there's an infinite number of solutions of this differential equation. And if this is a little bit hard for you to see, I just realized it might be, I'll try to do my best to draw it again without everything else here. So if this is t and this is x, then what I've tried to draw here in blue, more or less, is something that kind of looks like this. It kind of goes like this, and then on the bottom it kind of swoops down, and it kind of goes like that. That's more or less the solution set. All right, so what you try to do is you follow the exact same method. You have a differential equation, you want to find the curves of constant slope. So you take this derivative and you set it equal to a constant. At that point, you're going to get an equation that's going to be what we call the isoclines, which are just curves, sometimes they're lines, sometimes they're curves, of constant slope in our solution. You do the best to draw those different isoclines and draw the little line segments representing the slope, and then you connect the dots or connect the line segments to pattern your solution through there. What you get in the end is an infinite number of solutions. All right, all of them are valid to this general solution of this ordinary differential equation. When I choose an initial condition, what's going to end up happening is one of these solutions will be the solution going through that particular initial condition, because there's an infinite number of initial conditions, right? So there's an infinite number of solutions until I lock it in there. I'm Jason. I hope you've learned something in this section. It's something that's hard to learn from a book, because a lot of times in books you'll have the full-blown graph right there with all the hash marks and everything, and it's staring at you and you don't really know how they did it. But when you look at it one step at a time, you know the first step is to find the lines of constant slope, the curves of constant slope. Then you need to draw the little line segments. Then you need to kind of pattern your solution through it. And hopefully, by going back and showing you the very first problem here, where we actually solved one of these differential equations, and I'm trying to remind you that these general solutions always have a constant there, and that leads to an infinite number of solutions, that shows up in these graphs. Because I know the first time I looked at those graphs, it didn't hit me like, why are they drawing 95 different graphs here? How can that be the solution? Graphing the solution. Why do I have 25 graphs in there? Doesn't make any sense. That's because of this. And we've talked about that. So practice your problems, get a pencil and paper out. Don't be too precise about it. Just try to do the best you can. And I think you can learn a lot. And with some practice, you'll get fast at it. And you can see there's really not that much to it, but it is a little bit tedious.
Learn anything at mathandscience.com.